Okay, our next talk is by Alex Fink from Queen Mary University, and we'll hear about Matroid tautological classes in types A and B.
Right. Thank you, Melody. Thank you, organizers and everyone. So, yeah, this is a talk on work in progress. This will not be the title of the paper, but it hopefully should appear in the archive this summer. These are the names of the authors. Alex Fink is my name. Okay, so our work is this type B case. Today we'll talk mostly about the type A case and vaguely, but not precisely, state what we do in type B, but that's the right choice for 20 minutes. Okay, so the word Matroid is in the title. What's a Matroid? A Matroid is a combinatorial gadget that I guess was invented in 1935 or so to capture the similarities between notions of independent sets that appeared in linear algebra, graph theory, transcendence degrees of fields, these kind of settings. So the linear algebraic setting is maybe the one that comes up most readily algebra geometrically. So here's how that goes. Let's say I've got some field k, and I have a linear subspace of k to the n, call it V. And I want to look at how the coordinate hyperplanes intersect this. So maybe I can say, actually, I won't take the coordinate hyperplanes, I'll take their complement. And I will look at how, let's call it H for hyperplane arrangement complement. This will be the intersection of my linear subspace with this open torus. And the matroid, a matroid, is, you can think, some combinatorial data I can associate to this H that tells me a lot about this H. So I will leave a space for an adjective here, but the matroid of H is a set system. Well, it tells me how these coordinate hyperplanes intersect inside H. So what is it? It's like the set, let's call it M. It's the set of all subsets of indices of my coordinate hyperplanes of the same size of the dimension of V that index bases, that index hyperplanes that intersect transversely. Okay, so if I take V and I intersect it with the B indexed hyperplanes, I get 0. Okay, so example is called for. So, well, I'll draw the projectivization of V. So maybe V could be a 3 space in K5, and I could draw the projectivization of V. So that's a 2-dimensional space with the projectivization of H inside it. Well, H will be the complement of the 5 coordinate lines in K5. So, you know, maybe they look something like this. That's a triple point. That's a triple point, say 1, 2, 3, 4, 5. So 1, 2, 3, and 3, 4, 5 do not intersect transversely, but all the rest of the triples do. So I write down that set system, you know, I exclude 1, 2, 3, and 3, 4, 5, and the rest of the sets are my matroid. I got that one. So that's the kind of thing a matroid is, and you can learn lots about well, H or other algebraic objects from it. So, you know, you can write down, you know, point counts if your field is finite, or the cohomology with its ring structure if H is C, or you can use matroids to like compactify moduli spaces of these H. And you know, Seth and Melody both said the word matroid, so they've already given you 2 further applications of matroids in algebraic geometry in their talks than I was going to. So there are lots of applications of this particular combinatorial data. So it's a nice thing to have around. This is a class of matroid. These matroids are actually called representable, the ones that really come from linear spaces. So what's a matroid in general? Well, it's some kind of set system. So I have some sets. Well, what do? I want to combinatorially axiomatize what these look like. The definition you'll usually see is something like the Steinitz exchange axiom from linear algebra, but my favorite way to state it is polyhedral. So what do? You take the convex hull of the 0, 1 indicator vectors of your bases. So that's my 0, 1 indicator vector. And you look at the edge directions of this polytope. And in this case, well, I want the edges to be in directions EI minus EJ for some I and j between 1 and n. There's your type A root system. That is why this is the type A part of the talk. So, this is an example, but you also have examples which are not representable. So, for instance, here is a non-representable matroid. This is the non-Pappus matroid. Pappus's theorem in projective geometry, known by the Greeks, says something about how what happens if you have a hexagon and a conic, how its diagonals intersect. I guess I'll be drawing it dually. So, here are the 6 vertices of my hexagon. And now Pappus's theorem says if I consider these 3 lines, they should be incident. And if I say, oh, they're not incident, you can't actually coordinate that, but it's still a matroid. So, and these kind of existence of non-representable matroids is, responsible for what I think kind of one of the pieces of magic of matroid theory is. So, we have, okay, kind of symbolically, have the set of all matroids, and we have a smallish set of representable matroids within it. And, well, if a matroid is representable, you have some kind of variety. Maybe it's this one. And you can, well, that or other constructions lets us associate a variety to a matroid. And then from there, you can produce some kind of algebraic invariant of your variety. And the beautiful magical thing about these objects is that if your matroid is not representable, well, you may have to bypass the variety, but often you can still get the algebraic invariants which the variety would have had it existed, and they behave as they would have had the variety existed. And so this is a kind of a surprisingly recurrent theme in matroid theory. So the example this work is based on, I can now say, is the Fields Medal winning work of Junha, as of yesterday, where a particular variety and a particular algebraic invariant here. So what's the variety? It is the, okay, so I guess this is kind of Feichner and Sturmfels are who this part of the story is due to. The variety here is the wonderful compactification. Let's call it W sub m of this hyperplane arrangement complement. So I could just compactify it of its projectivization. I could just compactify it in like the projectivization of V, but I want to blow these various loci up and compactify it in a different way, a normal crossings way. And, well, from that, well, in the case where this exists, you can produce its Chow ring. And, well, I can call that, let me call that the Chow ring of M, for in fact it only depends on M. And the really great thing, the Fields Medal winning work, was that actually, the Chow ring exists, okay, that the Chow ring exists for every Matroid, that's still in Fechner and Sturmfeld, but the Fields Medal winning work is that, well, it behaves like it came from this thing. If my field was C, then this is a complex projective variety, so its Chow ring has all sorts of nice properties. It has Poincare duality, it has hard Lefschetz, it has Hodge-Riemann relations. Any Matroid, the Chow ring still has all of that stuff. So for any Matroid M, this Chow ring of M, June likes to call this the Hodge package. So as if it were a star of some x over C projective, has those kind of properties. And so the Hodge package lets you do things. Well, okay, the Hodge-Riemann relations says that the signature of the intersection form over the reals is such and such. From there you get inequalities, the Khovansky-Tessier inequalities and things like that. And you can use these inequalities to prove combinatorial inequalities by doing intersection computations that have some combinatorial interpretation. So this is a powerful new way to produce combinatorial inequalities about Matroids. So you get lots of conjectures like this. For example, you get the proof of a conjecture due to Rota and Welsh and others in various settings about the log concavity of the characteristic polynomial, more or less the Poincare polynomial of this thing over C. That was conjectured to be log concave. Its logarithms of its coefficients made a concave sequence. This proved it. So, okay. In some sense, this is what we want to do, you know. So, theorem stated far too vaguely. You're, myself, Larson, and Fink. Okay, extremely vague theorem. We want to do this kind of thing. I will do better than this by the end of the talk, but for now, we want to do this kind of thing in Lie type B. Okay, so, well, I mean, I pointed out a few of the things that are Lie type A. So how do I change those to Lie type B? Well, okay. Well, maybe here is the clearest thing. Here's the type A root system. So I can make my Lie type B analogs of Matroids just by putting the type B root system here. Those things that I get are known as delta Matroids. I will put in blue my Lie type B things. I can get delta Matroids this way. Okay, what do? I take my 2n+1 dimensional space with a non-degenerate symmetric quadratic form, and I take isotropic subspaces, and I blah, blah, blah. That will give me an example of a delta Matroid. And so the combinatorics exists. These delta Matroids are an example of something called Coxeter Matroid. You can do this for any root system, for any maximal parabolic in this root system. And top tip, if you are ever in an algebraic combinatorics talk and you're lost, but you still want to ask a question, your question should be, can you do that in other Lie types? So, okay, that's not just what we're doing. Delta Matroids have interest that isn't just from this, can you do it in other Lie types? Like they come from Matroid independent set systems instead of basis systems. They have nice origins in matchings in graphs or in graphs embedded in surfaces. So if you like these kind of graph theory objects, you have some reason to be interested in delta Matroids. The key type A thing which I want to change to type B though, is over here. And it turns out this thing always embeds in the toric variety of the type A Coxeter complex. So you take, what is that in this case? You take the hyperplanes normal to all the roots, and that gives you a hyperplane arrangement. You refine it to a fan, and that's the fan that gives you this toric variety. So, n equals 2, it's this kind of thing, right? And I'm drawing it modulo one direction. So this is my A2 fan. So that embeds in here, and then we get a nice class of this thing in my chow ring. Well, in the chow ring of here. And so there's another type A object that I can change to type B. So I can change this to type B. And what do I put here? So at first, we hoped there would be something nice to put here. If you've done, say, tropical geometry, you might have encountered this object. This object is the Bergman fan. The Bergman fan of this matroid, that's a Minkowski weight. It defines a class in toric intersection theory, so it lives in here. What do you put here? Well, there's no real satisfactory equivalent of the Bergman fan. I mean, maybe because this thing isn't n-dimensional. I don't know, the combinatorics just work out. There isn't really any nice analog of the Bergman fan. And so to give a theory that would talk about these delta matroids, we had to take a leaf from this work of Burgat, Ur, Fink, and Seng. That's on the archive last year, which is the tautological classes of tautological bundles in the title. So another instance of this kind of story, variety, algebraic invariant. What's the variety? Well, or the algebraic object? Well, it is a tautological bundle from a Grassmannian. So let's say I have a representable matroid still. This is back in type A. All right, well, I can take the toric variety of my matroid, of my polytope, and that embeds in the Grassmannian in the following way. Well, V represents one of the points in this Grassmannian. There's an action of an n torus on it. I can use that n torus to move around the point representing this V. And I take the closure, and it turns out I actually get the toric variety of my matroid polytope. And then xan minus 1 surjects onto that. And that is how you can get these tautological bundles. Here I have tautological bundles. Maybe I have the tautological quotient bundle or the tautological subbundle. And I can pull them back all the way across this, and I can get some kind of matroid tautological bundle and matroid subbundle living over here in the case where the matroid is representable. So this picture goes under the second bubble, and under the third bubble, well, okay, these are vector bundles. Okay, so maybe we could take Chern classes and put them in this chow ring, but we see more of the vector bundles if we take their classes in the algebraic K theory. And so their theorem is that they prove that you can construct classes of these bundles in the algebraic K theory, and then you can, do some nice stuff to steal some of June and others' positivity results and use them to say something about computations you do with these classes and associated Chern classes and whatnot in this K theory ring. In particular, I'd just like to mention the key technical element just because I love it. in particular, one of their theorems is kind of an exceptional Grothendieck-Riemann-Roch isomorphism between this K-theory ring and this Chow ring and a triangle. Grothendieck, or Hirzebruch-Riemann-Roch, I should say. Hirzebruch-Riemann-Roch is this case that says, oh, there's a way if I tensor with Q, Turing character gets me over there, and I can put a Todd class to make this and commute. And those are messy objects from a combinatorial point of view. They give a nice combinatorial different isomorphism where I can actually put Z here, and I can do some very natural Matroidy stuff here, and it's all much easier to handle combinatorially. And my time is up, so I'll say that our work is essentially this board in type B. You can put an orthogonal Grassmannian here, or various other things, get some tautological bundles. These things, these classes exist. This diagram exists. And if you're interested in, say, what we do with this to prove combinatorial inequalities, talk to me after the talk, but I'll stop there. Thank you.